Hi, Chem 11 students. All right, so let me show you how to do one of these stoichiometry problems that involves a limiting and excess reagent. The problems we were working on previously only would give you the mass of one reactant. So the way that this problem is different and more difficult is that it gives you the mass of both reactants. So here's a sample problem. It says, consider the reaction below. What mass of water can be produced if you combine 30.0 grams of pentane, which is C5H12, and 20.0 grams of oxygen gas? So what's tricky about this type of question is that these masses of the two reactants are not present in an amount where both of them would be completely used up due to the molar masses of each substance and the ratio in the reaction. So in the reaction, 1 mole of pentane is consumed for every 8 moles of oxygen. And so one of those is going to be a limiting reagent, meaning that the amount here is going to limit how much can be produced. So there are actually a few different methods to complete a problem like this, and the method I showed you in our notes and that I'll show you here is to try the conversion with both starting materials. Okay, because we're going to be doing mole conversions, we're going to need the molar mass of pentane and oxygen gas and water. So let me do that first. Molar mass of C5H12. By the way, in some of my answer keys, a few of you pointed out that sometimes my answer is off by point something compared to yours, and that can sometimes happen depending on which periodic table we're using to get the molar masses. So you guys have a periodic table that goes to 1 decimal place, whereas sometimes I've been using a periodic table that is more precise. So I'll try to, from now on, use a periodic table that is only to 1 decimal place, just so it matches the one that's in your book. Okay, so molar mass of C5H12, that's going to be 5 times the molar mass of carbon plus 12 times the molar mass of hydrogen. And as you know, we get these masses from the periodic table. So I'm just doing this on a calculator beside me. That's 72.0 grams per mole. The molar mass of oxygen gas is 2 times the molar mass of oxygen, and that will give you 32.0 grams per mole. And then the molar mass of water, because that's what you're being asked to find, the mass of water that is going to be 2 times the molar mass of hydrogen plus 1 times the molar mass of oxygen. Okay, so that's going to be 18.0 grams per mole. I'm just double checking something here. Okay. All right. So let's first try this problem using the 30.0 grams of pentane as your starting material. So trying this would be assuming that you have an unlimited amount of oxygen. And so I'll be explaining a little bit better later on how you decide which is your correct answer. Actually, something I'm going to put here is a general roadmap for converting from the mass of a reactant to the mass of a product. So you're generally given the grams of your starting material, and you would first convert to moles of that starting material. Then using the mole ratio in the balanced equation, you would convert to the moles of your product, of which the mass you're being asked to find. So in this case, that is water. And then you'll convert that to the grams or mass of water. Okay, so we're going to go through that process for both of the starting materials that you are given in the problem. So first, using 30.0 grams of C5H12, we're going to convert that to moles using its molar mass first. And so 1 mole of C5H12 has a mass of 72.0 grams. So this conversion I'm writing here, I know it's not the best for formatting because I'm typing it out, but that comes from here. So here, the way it's written is mass over moles. But here I've written it as moles over mass because I want mass to cancel out and I want to convert to moles. Okay, so make sure that you're multiplying by conversion factors that are in the correct format. Next, I want to convert to moles of water. And so that's going to be based on the ratios in the balanced equation. There is a coefficient of 1 in front of C5H12 and a coefficient of 6 in front of water. Because I want to convert to water, I'm going to start by writing 6 moles of H2O, and that's over 1 mole of C5H12. Okay, and then I want to convert to mass of water. So I'm going to be using the molar mass of water. Oops, I need my cursor here. 18.0 grams of water over 1 mole of water. And let me just change the size so that's all in one line for you. Okay, I recommend that before you determine your answer, you just double check that everything's formatted correctly. So here, mass of C5H12 will cancel out, and then moles of C5H12 will cancel out, and then moles of water will cancel out, and you'll get an answer in grams of water. Mathematically, you're going to do 30 divided by 72 times 6 times 18. So let me just do that in the calculator for a moment. So again, 30 divided by 72 times 6 divided by 18. And let me try that one more time. I think my calculator gave the wrong answer. So 30 divided by 72 times 6 times 18. There we go. That looks more reasonable. I'm just gonna check that one more time because my calculator messed up the first time. So 30 divided by 72 times 6 times 18. Okay, so 45.0 grams of water. That is how much water you can produce if you're using 30.0 grams of pentane and assuming that you have enough oxygen gas. But let's now try this with the amount of oxygen that you are given. So instead, actually let's change back to this size. I like this size font. So using 20.0 grams of oxygen gas. Okay, 20.0 grams of oxygen. I want to convert 2 moles of oxygen. So I'm going to write that 1 mole of oxygen has a mass of 32.0 grams. Then I want to convert 2 moles of water. So in the balanced equation, we see that there is a coefficient of 6 in front of water and a coefficient of 8 in front of oxygen. So I'm going to put 6 moles of water over 8 moles of oxygen. Let me just zoom out so you can see more of the problem and the work. Okay, then I want to convert to mass of water. So just like we wrote in our previous conversion up here, 18.0 grams of water over 1 mole of water. Okay, let's double check that the conversions are set up properly. So mass of oxygen will cancel out, moles of oxygen will cancel out, and moles of water will cancel out, and you'll be left with mass of water. Okay, mathematically, you're going to do 20 divided by 32 times 6 divided by 8 and times 18. So let me do that in the calculator. Okay, 20 divided by 32 times 6 divided by 8 times 18. Okay, 8.44 grams of H2O. So that's how much water you can make if you have 20 grams of oxygen, assuming you have enough of the other reactant. So having a look at those two results, let me just highlight both of them. Oops, that's just not highlighting. Okay, here we go. All right, so let me note some things here. This one is the larger value of water. And this means that C5H12 is the excess reagent. I'll explain it a little bit better in a moment. Here, this is the smaller value, therefore O2 is the limiting reagent. So to explain that a little bit more, I'm going to enlarge this. Again, this is how much water you can make with 30 grams of C5H12. This is how much water you can make with 20.0 grams of O2. So if in this reaction, you're combining this amount of C5H12 and this amount of O2, the amount of oxygen is going to limit the amount of water you can produce greatly. Okay, so you actually can't produce this amount of water because you're limited by the amount of oxygen that you start with. Okay, I'm gonna highlight this part just to emphasize which is the excess reagent, which is the limiting reagent. And let's write our final answer. So again, in this process, your final answer is always going to be the smaller of the two values because one of the reactants will limit how much of the product you can make. Okay, so let's write, therefore, 8.44 grams of water can be produced. And that would be your final answer. Okay, so there we go, there's the problem and all of the solutions. So I will post this document on the Scholastic portal, and as always, please email me if you have any questions. Hope you're doing well, take care.